All right, so then if you've installed, then you want to type library, parentheses, foreign, now without quotes, highlight that line, and run it. Now, when you run code, it shows up down in the console window. Notice it looks like nothing happened. Something did happen. There were no errors given. That means that it basically put this library into my active environment so that I can use functions in that library. And the function that I want to use is read.export, X-P-O-R-T, to read in the .xpt file. So when I downloaded that file, I put it onto my desktop. It was called, I had the one with the PFAS data in it called PFAS_J.xpt. And I have to put that in quotes exactly how it's named into this function. And I need to store this into an object. So I made up a name that I thought was appropriate called PFAS. You can call it whatever you want. You can call it Joe if you want. But my object is PFAS, and R is going to read the data in that file and store it in this object called PFAS using this read.export function. And the equal sign facilitates that. So I do that. Again, it just, in the console window, it just put what I have up there. Nothing happened. There's no errors. But actually something did happen. That data is now stored in PFAS. If you want to see what's in PFAS, you can highlight just PFAS, that object name, and just run that, and a whole bunch of data shows up in the console window. And here are those codes, so I can go, let's see, look at this metadata file. And LBXPFDE, that's perfluorodecanoic acid concentrations at nanograms per mil in this individual 93706. Okay? Great. Now I can do the same thing with the demographics data. And there we go. I can look and see what's in the demographics data. There's a whole bunch of data in here. And I would have to go look up that code, but here's gender. And there's just 2 and 1s. 1, 2, 2 and 1. 1 stands for male, 2 stands for female. Now at this point, if you said, I hate R, I don't want to learn any more R, I want this program to go away, you could simply save this as a .csv file, which you can open in Excel by typing write.csv, and then the name of the object you want to save, which is PFAS. Now, just so you know, PFAS is a table. And then I have to, in quotes, give it a file name. What do I want to call it? I'll call it PFAS. Call it PFAS NHANES 2017-2018.csv. Write.csv, parentheses, PFAS, comma, and then whatever name you want to give it. And there. Run that. And let me look at my desktop. There it is. And I can open with Excel. There it is. There's all the data on PFAS 2017-2018 NHANES data. Go ahead and do do what you want in Excel with that data. But I'm an R user, so I'm going to use R. And I want to calculate some simple statistics on PFAS chemicals in these people. And I'm going to merge these two data sets, the demo and the PFAS, because I think it'll be easier to work with. And one of the reasons I'm going to do that is because although the demographic data has a certain number of individuals in it, there's not the same individuals that they got PFAS data for. And so one of the ways I know that is I can say n row, how many rows, n row PFAS. So how many rows of data are in PFAS? 2,133. N row demo. I don't think these are the same. Yeah. So they didn't measure PFAS in all of the people that were in the study. Okay. So I'm going to merge these two data sets based on the identifier number that they gave individuals in the data set. And so it's only going to, this function only going to return to me data that's common for those individuals in these two data sets, demographics and PFAS data. So I do that, and then be hard to look at merge because it's pretty big. But this is the demographic data. See, there's lots of NAs, so they don't have data for everything. And then this is the PFAS data. And so it's matched demographic data, PFAS data for each individual that's in the study. All right. Now I'm going to ask, what is the mean concentration of a given PFAS chemical in males versus females? All right. So the way that we can do this is using a subset function in R, which is just simply a bracket. And a comma goes in the bracket. On the right side of the comma, I indicate which columns of data I want. On the left side of the comma, I indicate which rows I want. If I put nothing for columns, it'll give me all of the columns in that data set. So I want all of the columns, but I want rows that match males, data from males. Well, one of the nice things with RStudio is if you typed the object name and it's a table, a data table, you press a $, it pops up with all of the columns there. And if I scroll down, I know that that's gender. So if I were to just run that, that would give me all of the data on gender from our merged data set. I only want males first, so I'm going to say merged, subset with the bracket, merged this column for gender, give me ones that equal 1. So only give me data where the gender matches 1, which is males. So give me all of those rows where the gender column matches 1, and give me all of the columns from those rows. I can do that. It runs, no errors. I can look at males, and somewhere here's the gender column. Gender. They're going to be all 1s. Okay? Do the same thing with females, only now the gender column matches 2. Okay? So there we go. Now, you can use the same kind of this, $sign here by looking at males, and I'm going to select all of the data in a column that corresponds to this PFAS. What is it? LBDMFOS. LBD. There it is. That's the perfluoromethylheptane sulfonic acid isomers. You could sum them all up and do the total concentration. I'm just showing it for this one. So for males, then I select this column using that $sign. Okay. Again, if you just typed males, that's our table for males, and the $sign, and then you can select whichever one you want to look at. Let's look at that one. And we have to tell R to ignore NA values, otherwise it will just return NA for a mean. So we do that by putting in this extra argument here for the mean, and this is how you calculate a mean, was strangely enough, mean. NA.RM equals true. Remove NA values before calculating the mean. Do that, and there's the mean for males, 0.01 nanograms per mil. I can use the same arguments, only this time using the SD function, and get a standard deviation. So it's 0.01 plus or minus 0.1 nanograms per mil for males. Do the same thing for females, and females are much lower for this particular PFAS. So we could do the same thing looking at all of the different PFAS compounds and characterize, whether males or females had higher levels. What if we wanted to plot by age category? Well, it's very easy in R to do this. One of the things you might want to do first is look at what ages are there. So R has a function called hist, and so I have ages here in this column. Again, using the $sign to select that column in merged. So that's the data I want to look at. All the years, ages, and years. And I'm going to say make a histogram of that. And there it is. Fairly even distribution of ages, but as was said in the video, younger ages not so much. So it starts at age 10 and goes up to like 80. So then I made some age categories, and the way that I did that is again by subsetting the data in merged using the bracket. And I said in the column for ages and years, only give me rows where the age is less than 20. And then for a column, return the identifier number of the individual, which is the first column. It's column 1. Similarly, for my second age category, I said give me ages that are equal to and greater than 20 and ones that are less than 30. So that age category will be 20s to 29. And I didn't say less than or equal to, I said less than 30. So I can do the same thing for further age categories to get 30 to 39-year-olds, 40 to 49, 50 to 59, 60 to 69, 70 to 79. And so now I have the identifier numbers for those people that had those ages. Okay, so these are just their identifier numbers. So these are people. These are all people that are less than 20, and we know that there's only 10 and over, so it's 10 to 20-year-olds. All right. Here then, I say in the merged data, give me all of the data from that merged data set where the sequence number is the same as in the age 1 category for people. This little in argument. So give me the merge data for people that are 10 to 20, or in other words, that match these identifier numbers. These identifier numbers matched what's in the identifier numbers in our big merged document. And I can do that for the first age category, second, third, and so on. And so I will get data from our merged document that is for each of these age categories. All right? Almost there. So then I said, okay, for each of those ages, I want to get data from this PFAS compound. All right? So here's the data for age 1 category. Using the $sign, I select the column that has the data for this particular PFAS. And now I'm going to make a vector of all of these. And a vector is basically all of the data in order from top to bottom, starting with data from age 1 all the way through. It's just one long series of data. I then make categories for each of these, a category number, a 1 for the first age category, and I replicate the 1 the same number of rows I have for age 1 group. To do that, I'm going to make a category, and here if you look at the category now, I have a bunch of 1s. I have a number of 1s, the same number of rows in the age 1 category. And now I'm going to put them together with this cbind function, column bind, put these together in columns, the categories with the data, and I'm going to store it in an object called box data. And if you look at that now, I have the category, the age category, this is 2 and the data, the PFAS data for that age category. Now, I didn't make a table, and it didn't make a table because the number of data that we have for each age category is different. So they wouldn't have the same number of rows. So you couldn't make a matrix out of it. So it has to be in this vector format. And now I'm going to make a box plot out of this data. I got this is the column name for the PFAS data. This is the category, the age category. That's the column label for the age category. All of the data is in this object called box data. With the names argument and box plot, I can label it with the names. I can give the y-axis a label and the x-axis a label. And run all of this, so I have to highlight all of this and then run it. And here is now my plot of age categories for this and the concentration of each chemical. Now, a couple of things to notice about the data. First of all, a lot of these are all outliers. Box plots, the circles indicate outliers. We have a lot of low concentrations and a few higher concentrations. That's a log normal data. That follows a log normal distribution. A lot of chemical concentration data follows log normal distributions. And of course, the other thing that you can see about it is that as we age, we accumulate more and more of these perfluorinated compounds. I know that's a lot, but I'm giving you this script, and just replicating things in that script, you could pull out data from any NHANES database. You could pull out concentrations of whatever they've got in there. Or if you don't want to use R, you can save it as a CSV file and use Excel. Completely up to you. And then I hopefully have the screen recording going so you can, if you want to get data out, you can export it from our studio, save as a PDF, save as an image. You can select Zoom, and you can save it here as a PDF as well. So there's a few different ways of getting that data out. Okay, so give it a shot. If you pick a chemical to do your project on, it's not appropriate for getting no L's or low L's, but there's NHANES data. You might be able to use that to back calculate the dose, the exposure dose, for these individuals anyway.